Yeah, my name is Ancla, and today I will talk about the results of my master's thesis I did at the Astronomical Institute in Bochum in collaboration with the Max Planck Institute in Garching. You can find a preprint of the results on arXiv. That's why you see this image. Yeah, the basic idea of my master thesis was to investigate physical commonalities of multifrequency data over the whole electromagnetic spectrum without the usage of any theoretical models. Therefore, we used, the information measured by different all-sky surveys. Is it okay with the microphone? Okay, you hear me. And due to the high dimensionality and the number of different vectors, we used a Gaussian mixture model to get access through the data structure and analyze it further with probability theory. So during the talk I will talk about the verification of this method based on simulated data sets and show some exciting results on real measurements. So what we basically use is the Bayes theorem. You can find here. The output of a Gaussian mixture model is, of course, a joint probability distribution, which we can use to directly compute a conditional probability distribution. So we can use a Gaussian mixture model to directly compute images from the information I learned during training process with a Gaussian mixture model. In our case, we had, for example, the case that X is represented by the emission in the gamma ray regime and Y is represented by the emission in other frequency regimes like the radio and infrared. What we also had were M different feature vectors of that, so we have different number of pixels in the images and we have to reduce this on the same number. So let's just have a look at how we verified it. So we just started to simulate different galactic all-sky maps based on of known galactic structures. So let's just have a look at it. I have 3 different models at this point. This is one of the 6 maps I used for Gaussian for training with a Gaussian mixture model. This is another, and this is also another. You can see it's diverse, but it's also all of them are in the same resolution. So what we first asked is how good is a Gaussian mixture model in reconstructing the real input data at this point. So let's have a look at the first map I showed before. And now I trained the Gaussian mixture model with all these 6 data sets and repredicted this map by the usage of the other 5 remaining maps. So and this is the reproduction. Just concentrate at this point and here. That's I also compute the difference for it, but you see at the scale, if you just look at the scaling, these are really small deviations. So we just find that if we have the same resolution, we are able to repredict the structures at this point. So what we further asked is how the Gaussian mixture model deals with unobserved areas, which is always typical in astronomical data that not all areas are observed. So I just left data during training. So again, the first map. And I forgot information of this map during training. The other maps are fully used at this point. So the first test case was just to use the information of the disk. So by repredicting this, we get this result. So what we find is that by using only the information embedded in the galactic disk, we can reproduce somehow the galactic disk, but we are overestimating the unobserved areas. So that's the difference map. We can see this quite easy. But what we then did is we used the information for training embedded in the disk, and only one small part of the southern hemisphere, just this small part for training, and we got this result. And that's much better. But if you look in detail, you can find that in the top of the image there are somehow overestimated structures. So you can see this more easy in the difference map. So when you imagine the difference map before, we have this discrepancies and somehow this, but these black discrepancies are new. This is just what we missed when we are just using the disk information and somehow some part of the background. So what I then did, just for completion, I used half of the information for prediction, again this map, and what we find is that it is in well agreement with the information we used, with the whole information used for training. Just to be complete, this is a difference map. What we further asked is how good the Gaussian mixture model is in improving resolution. So before, all these all-sky maps had the same resolution, and now, again the first map, I just used a Gaussian kernel to smooth this map, to cut out the small-scale structures, and used this map and the 5 remaining maps in full resolution for training. And what we get is this reconstruction. And what we first think is that it's okay, I think. But when you look in detail, and maybe I will show the power spectra for that, when you look in detail, you can find that the structures that are predicted are in really good agreement with the real structures we expect in the image. But, and that's the main problem, the magnitudes of these structures are underestimated. And that is what gives you the feeling of it's okay. But the structures are real, and we can find this by using a Gaussian mixture model. So how can we use this approach on real data? So just a short look, what was my data sample? I used different all-sky maps from the radio regime, for the Planck survey, you all know, I think, infrared data, the Akari data we here heard about this morning, the H-alpha Finkbeiner map, and the Fermi data. And so what we can see when you just look here, they are in quite different resolutions. So what I first did was to homogenize the data, just fix negative calibration residuals to use logarithmic magnitudes during training. Then I also cleaned the data, just remove artifacts and point sources from the data sets, and also unificate it, just that I have at the end the same number of pixels for training. So let's first have a look at the X-ray data set. That is, I don't know, that image is somehow known for some of us. And I just to show the cleaning process is somehow I just cleaned it from these sources. And this map I used for training. And I used this and 37 other data sets during training process. And for prediction of this map, I marginalized this information over the whole X-ray regime. So I did not use any redundant information for prediction. And this is our result. So what we can see is first that these dark filaments in this region, just look here, are much higher resoluted now. We just switch it a little bit. But of course, that's what you first see when you look at the image. These structures here, and somehow the structure here is not really reconstructed at this point. So what we find at this point is that the X-ray regime has at least one component embedded which is not reproducible from the other frequency regimes at this part. But however, let's just have a look at the gamma ray sky. What was the first idea of my thesis? To try to sharpening up the gamma ray sky by the usage of the higher resoluted all-sky mass, because this is a data sample which is at worst resoluted these days. This is somehow the original Fermi data, which was analyzed in the Selig et al. Paper 2015, where they deconvolved and decomposed the gamma ray sky in somehow 9 of these frequency maps, and this is just one from the data sample, and now I try to reconstruct it, to sharpening up the resolution at this point. And this is somehow an amazing result, because this is a sharpening up prediction at this point, and you can see that if you look here or somewhere here or in these regions, that the structures are now highly resoluted from the other data sets. What we also found, of course, that if you look here at the Fermi bubbles and in this region, that this structure cannot be reproduced at this point. What I missed to say until now is that this analysis is only done with 3 Gaussian components. We have 37 dimensions, 2000 different feature vectors, and only 3 Gaussian components. And when we improve the number of Gaussians, we can improve the reconstruction of faint emission. So what I just did is to improve the number of Gaussian from 3 to 18. That's just the difference map. And we found a better reconstruction of the Fermi bubble. Just have a look at the difference map. There we can see that we find that at least parts of the Fermi bubble is encoded in other frequency regimes at this point. What was also did during the analysis of Selig et al. 2015 was to decompose the gamma ray sky in a claimed hadronic component and in a claimed leptonic component. And with my analysis, I tried to verify these claims and also to higher resolute these images. So this was the claimed hadronic component. We have, of course, low resolution and these unobserved areas at this point. And this is the reprediction of this information. For this training set, I did not use the information of the other Fermi data sets, because this would be a redundant information, and this is not used. So we find that the hadronic component can fully reproduce at this point. And what we also did is to analyze its composition at this point. And therefore, I just used, you see slightly differences, therefore I just used the information embedded in the infrared regime and in the Planck high frequency regime, just representing dense dust regions. And so at this point we verified the assumption that this component is hadronic nature. Yeah. Just to show what happens when I use the other frequency regimes, it doesn't work so good. We have high discrepancies at this point, so these components are not necessary to verify the hadronic component. So let's just skip this because of the, who of you who are interested in the results can have access on this web page? I don't know what happens now, but it's there. On the web page, there you can find all the PDFs you have seen and much more that are in a paper, and you can also have access to the FITS files so that you can do further analysis with it. Yeah, let's just shortly conclude it. I showed that the Gaussian mixture model in astrophysics is a powerful tool to predict unobserved areas, to higher resolute data, and of course to heal imaging artifacts. Yeah, what can further be done? For now, I have not used any theoretical information, so we can just investigate physical priors to improve our results. Yeah. It's okay. You can read it.